Hey everyone, this is a late video for Short Text 115. This was supposed to go out Friday, so it's not really a preview. I guess it's a post-view or a review of what we saw then on Friday and on day 5. So electrical force, that's our first installment, our first discussion of electricity. And so week 1, day 5, electrical force, and the main equation here is this is Coulomb's law, which governs the force between 2 point charges. And we defined a point charge as something that has no internal structure, and so there is this property then we call charge, and it's ultimately defined by the experiencing of these forces, of this type of force, the electrical force. So between 2 point charges that are held at a distance r12 apart is then given by this formula. So the force, the magnitude of the force is a constant times q1 times q2 divided by r12 squared. So it's directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. So that's the magnitude of the force. Now forces are vectors, and so we need to talk about the direction of the force, and the force is along the line joining the charges. So what does this mean? It means that this force is the force, if you want, on charge 1 due to charge 2, and so it's a force on this charge due to the other one, and it's along this line joining the charges. Now, if the two charges are of the same sign, then the force will be repulsive. So it means it's going to point out in that direction. So if this is positive and positive, then it's going to be repulsive. If this is negative and negative, it's going to be repulsive as well. And on the other hand, if the two charges are of different signs, they're unlike signs, so positive and negative and positive, then the force will be attractive. And so in that case, the force will point towards the other charge. Okay, and of course we have Newton's third law that tells us that F12 is equal to F21. In other words, the force on 1 due to 2 is equal and opposite to the force on 2 due to 1. So that you know very well because you understand Newton's laws. So based on that idea, historically it became a question: how do these things feel the influence of each other if they are a distance apart? And so this question of action at a distance led to the concept of electric field. And so the way we understand this today is that given the existence of a charge, a point charge somewhere in space, then that charge generates an electric field everywhere in space around it, and that electric field will be will have this magnitude, will be the same constant we had before, which we defined in class, times the magnitude of the charge divided by r squared, and this r squared is the distance between the charge itself and the point at which you're looking. Yeah, so that's the magnitude. So if we have our point charge here and you're looking at this point in particular, then you have to measure the distance between those 2 points. That's what goes in here, and you calculate the square of that distance. You multiply by q1, multiply by this constant, and that gives you the magnitude of the field at this point. What about the direction of the field? This is a vector field. So well, if the charge is positive, then the field points away from the charge. So at this point, it would point away, directly away from the charge. And if the charge is negative, then the field will point toward the charge, and so it will point directly in that direction. So if you want radially toward the charge, and so sometimes we use this language then, and we say that a positive charge is the source of the electric field, and the negative charge is the sink of the electric field. This is a language that is inherited from fluid dynamics, where we talk about sources and sinks. Yeah, so that is points from where fluid is emanating and points where the fluid goes. And so, but of course, there's no fluid here. This is just language that was inherited from fluid dynamics, but we do talk about sources and sinks, and sometimes it's helpful to think about that, to remember that a positive charge is a point where the field comes out of, and if you have a negative charge someplace, then the field goes into an electric and that negative electric charge. And so then we say that then our charges, generally speaking, generate a field, but a field could point out of the charge or into the charge. And if you have more than one charge floating around, if you have q1 here, maybe q2 over here, q3 over here, then the field at any point in space is given by the sum of the fields due to all the charges around. So we're going to see a little bit more of that on Monday. So that's about it. That's all I have for you at the moment.